takeoff, sir.
Okay, so we're going to discuss propagation and antennas tonight. With a technician licenses, there's still quite a broad range of bands and frequencies and things to work. But it helps to know a little bit about why things happen. I get asked questions frequently about why I can only hear one half of the conversation, or how did Big Cabin come in on my DMR radio when it's northeast of Tulsa? And it's all about the propagation. So we'll give it a go. Radio wave propagation, getting from point A to B. Radio waves propagate in many ways, and it depends on the frequency and on the characteristics of the environment. And we're going to talk about three basic ways: the line of sight, the ground wave, and the sky wave. VHF, UHF handhelds, which are probably going to be most everybody's first radio when they get started, not necessarily, but frequently, are primarily line of sight devices. So radio energy can travel in a straight line from a transmitting antenna to a receiving antenna, and it's called a direct path. Not necessarily always direct, but that's the definition. There's some attenuation of the signal, like inverse square law, like a light bulb. If you're further away you get from a light source, the dimmer it gets. Radio waves do the same thing. You start out with hundreds or thousands of watts of energy at the antenna, and as it spreads out, it ends up being millivolts on a receiving antenna somewhere. So that's just a normal part of it. Direct path propagation is the primary propagation mode for VHF and UHF. Ground wave, when you radiate from your antenna, the signal will cross along the ground for a time. Excuse me. When you're at very high frequencies, curvature of the Earth, your line of sight limits the amount of range you have quite substantially. At lower frequencies, and like in the HF bands, especially the low HF bands, the radio wave can follow the Earth for a considerable distance, and it'll go well beyond line of sight and operate for up to a few hundred miles. Those of us old enough to remember listening to Chicago at night, WLS, that's all ground wave from nice low frequency, medium wave AM signal.
Don't forget WOWO.
The higher you go in frequency, the less of this you get. So the ground wave is, again, for VHF, UHF, it's 7 to 10 to 20 miles, depending on where you are. And it's why a repeater with a high antenna is so important. You can get a straight shot to that antenna, and it can, again, shoot back out, extending your range 4, 5, 10 times. Now, radio waves can be reflected by any conductive surface. That's water, ground, buildings. It acts like a mirror, and they bounce the radio waves around. Many of us had the dish antennas for our TV, and just a beautiful reflecting and focusing device. That refraction or bending occurs when waves encounter a medium having a different speed of light, such as water or an electrical feed line. Now, if you ever poked your fishing pole into clear water, probably not Thunderbird, but someplace where you could see into the water, you notice that the rod appeared to bend at the surface of the water. And that's the refraction that occurs because of the different densities of the medium that the light's traveling through, and radios do very much the same thing. The feed line also has an effect basically on the velocity. It's just about the speed of light being. It's not necessarily 300 million meters per second and everything. It varies with the density of the material. And the refraction of light in the lenses of an eyeglass are a classic example. If that didn't happen, folks like me would be in big trouble. Diffraction is when a wave hits a sharp edge, a corner of a building or the top of a sharp structure, any sort, and it causes knife edge, what they call knife edge propagation, or this signal that we see on the right side of this graphic. And if you're moving through it, you will hear the signal, then you won't, and then you will, and then you won't, and you get an effect basically called picket fencing. So on the slide here, sorry, bouncing around a little bit too much here. You get a picket fencing effect from that, but that's because of the diffracted signal that goes around the building. And sometimes it's just a combination of, in the case of downtown, some place where there are a lot of tall buildings, it's just be reflections and bounce off the various buildings could probably give you a similar effect. Now, the line of sight, the story about line of sight is mostly true. You get a little bit better distance with VHF and UHF because there is a slight amount of refraction, so that it does follow for just a little bit the curvature of the Earth, and it extends the radio horizon a little bit further. There are a lot of stories that are told about when we go through some of these things that aren't always necessarily exactly true, but if the gist of it that really counts. Now, UHF signals penetrate buildings better than high frequency or VHF because of the shorter wavelength. They can get it through the window easier. It's like a skinny burglar versus a fat burglar. So you get a little bit better penetration into the building. Now, buildings can block line of sight, but you can reflect or diffract radio waves around the building or over the building, and sometimes still make contact. Again, on the various reflections, especially with buildings and such, you can get multipath signals, and the tiny little bit of difference in the traveling distance is just enough to create some interference. And again, you can get picket fencing or fluttering or other distortions as a result of multipath distortion. A tropospheric propagation is in the lower, early in the weather, in the troposphere, in the lower level, 30 up to about 30 miles. Your radio waves can be reflected or scattered by clouds and rain, and density variations due to temperature inversions and such, and extend range out to about 300 miles. I had a query last night about picking up Big Ben DMR repeater in Oklahoma City on a handheld with a rubber duck antenna. And there's a good possibility it might have been just this very thing. Temperature inversions, weather fronts, they form ducts that trap and conduct the VHF and UHF radio waves for hundreds of miles. And if we look at this diagram, the very lowest level is our troposphere, and that 30-mile range, and that's where virtually all the weather is. And that would be the area that would give you the tropospheric ducting. Getting into the ionosphere, from 30 to 260 miles, and I've heard it or read that as much as 300 miles, but for the sake of our exam, it's 260 miles high. The atmosphere is thin enough for the atoms to be ionized by solar ultraviolet radiation. And ions are just molecules that have had an electron stripped off. when they get hit by the ultraviolet, it's enough energy to knock them loose. If you go back to your chemistry and valence and all of the atomic structure, basically the loose atoms that hang out farther from the nucleus of the atom tend to be knocked loose easier. The level of ionization that occurs high is because we don't have much air. There's not much density up there to block the sun's radiation, and so it really rips a lot of electrons loose, creating ions, ionizing the ionosphere. For obvious name fits obviously for that. And again, the ionosphere, once you begin to get up into the upper layers, we're not going to talk about D layer very much, but you can think of that as a daytime phenomenon, and it tends to go away at night. It goes away at night, and the E layer gets weak, and the F1 and F2 layers will combine. So the whole characteristic of the ionosphere changes between day and night. And again, with the density of the atmosphere filtering some of the energy from the sun, you get different amounts of ionization. It does also vary by hour and by the intensity of the sun's output. When we're in a solar maximum, there's a much greater amount of ionization that's going to occur than at the minimum that we're just gently climbing out of. It's a great time to be coming into the hobby because the conditions are going to be continuously getting better because of the solar cycle. The higher the ionization, the more refraction you get, the more bending of the radio waves, and the better your opportunities for long distance communication. The ionosphere as an RF mirror. It's not really so much a reflector as a refractor. The ionosphere can refract or bend the radio waves back to Earth, but it is like a reflection. It acts like a mirror. Most of the refraction at our frequencies occur in the F layer. And that reflection, the amount of reflection you get, is dependent on the frequency and the angle of incidence. If you're shooting straight up at a high angle, or your frequency is high enough, it'll just blow right through the ionosphere out into space. You get a case of ET call home. A very high frequency or a very high angle will cause that to happen. Skywave or skip propagation is responsible for most of our over-the-horizon propagation on HF and low VHF. And that includes 6 and 10. As a technician, you have full privileges on 6 and some significant privileges on 10 meter. And these will only get better and better during the sunspot cycle, increasing output of the sun. Skip is rare at 144 megahertz and higher UHF bands. There's still more line of sight. Each ground to sky ground trip is called a hop or a skip. You got if you're listening in Oklahoma City, again, I've had the question asked, well, why can't I hear both sides of the conversation? The fact that the skywave skips over a large amount of area means that people down there can't get it. But if two people happen to be on a coincident area where their skip beams land, they'll hear each other just fine and have plenty of time for a conversation. But I frequently, when I'm on the radio, I hear East Coast and West Coast just beautifully. They're bouncing right through Oklahoma. We're part of their hop in the middle of the 2-hop run or something. So sometimes you'll get both sides, but frequently you won't, or you'll just barely be able to hear the other guy talking. That's why when you're getting ready to call CQ, you need to wait a while and be sure that you don't have somebody out there really ratchet jawing and taking a long time on his turn, or you might break in on a conversation. And the signals can take many paths through the ionosphere, and that sometimes means that they'll randomly combine at the antenna, at the receiving antenna, and they can cancel each other or create irregular fading as the ionosphere changes. And when the bands are moving, you can really hear this. The resulting echo and flutter distorts speech and CW. And if you can distort CW, then data errors will increase. So it'll cause fading, will cause data errors in your digital modes. Highly ionized patches of the E layer can reflect HF and VHF signals, including 10, 6, and 2 meters, the so-called sporadic E. And when the aurora is really up, you can also reflect, and you'll get reflection and scatter through the aurora effect at the north and south poles. And it'll get VHF and UHF and give it a very distinctive sound, distorted sound. Now, meteor scatter, we've got meteors, thousands of meteors centering the atmosphere every day, and most of them are tiny. Some you can see, but they leave trails of highly ionized gas that acts to refract your radio waves, but they're very short-lived, only for seconds. And the trails can reflect radio waves. It's called meteor scatter. And the best band is 6 meters. And 6 meters has got the nickname the magic band because it comes and goes in I guess in interesting ways. So I'm told. I'm about to finally get on 6 meters myself. I haven't had a radio till recently that would go there. This is mostly in the E layer, meteor scatter and sporadic E. They'll support contacts up to about 12 to 1,500 miles. Sun cycle. The level of the ionization depends on the intensity of radiation from the sun. That radiation level varies intensely with the number of sunspots on the sun's surface. And we are thankfully at the end of a very quiet solar minimum, which had many, many days without a sunspot to be seen. And we didn't benefit very much from that from propagation standpoint. So the high number of sunspots results in high levels of ionizing radiation emitted from the sun, and consequently the ionosphere gets very activated. And sunspot activity is commonly known to be an 11-year cycle. There are some additional cycles that apparently run for greater minimums and maximums. And apparently we've been in one of the more significant minimums in the last cycle or two. Good news is we're in cycle 25 and ionization is increasing and we're starting to get some better numbers. I'm hearing people talk that 15 is alive, and I mean 10 and 6 are going to wake up, and it's going to be a great time to be on the air. Okay, that's at this point. If we have any questions regarding that, would be a good time to go ahead and ask. I'm going to review this here just for a second. That pretty well covers the materials that you need for your exam, and certainly in the book, it will fill in any other gaps that there might be.
So the text talks a lot about signal propagation, temperature inversion, charge ions being beneficial. Rain, other phenomena, solar flares like that, those disrupt the signals, but is that talked about anywhere on the exam?
Okay, I'm sorry. Should you say that last part again?
What does the exam go into what weather phenomena are decreased signal propagation?
It's not, there's not a lot in there on this. I'm going to include a couple of PDFs, one on antennas and feed lines and another one on propagation. And essentially, well, the questions would be, let's say, for example, if you were going to listen to weak signal, 2-meter weak signal propagation, that would normally be a single sideband, horizontally polarized situation. It does talk about things that can cause weaker signals, and we will talk about polarization a little bit in antennas, and your signals are polarized vertically or horizontally or anywhere in between, depending on the ionosphere. So short range, if you're not in the same polarization, you get cross-polarized, you get a lot of attenuation because of that. And there are questions regarding that. Looking to see what else we might consider on that. Fog and rain don't have very much effect on the lower band, on the 6 and 10 meter and the HF bands, but it does affect VHF, UHF more and microwave more. We know that because when they gave us digital TV in UHF, a little bit of rain could blank your TV out real easy. They do ask about what the band frequencies are in general, VHF, UHF, and HF. And that's something to be aware of, and the speed of light, something fundamental to be learned. It's pretty outside of beyond the things that we discussed in the slides. There's really not a great deal more on the exam that you find that it'll be tough to figure out.
Yeah, they'll throw in the speed of sound as one of the choices.
Say that again.
They'll throw in the speed of sound as one of the choices.
Yep, as a distractor.
Yeah.
Yep. Yep. We're not worried about the speed of sound, that's for sure. Not at this point. Any other anything else that I can expand on that?
Nope.
Okay, when we get into antennas, there's a lot of, I'm going to step back here. Yeah, okay. There's a lot of emphasis on really fancy, expensive antennas. But the truth of the matter is, if you can connect your radio, your transceiver, to anything metallic or anything that'll conduct, and do it in a manner that it won't blow up the transceiver, you can transmit, you can get signals out, and you pick signals up. Obviously, the better the antenna is, the better matching you have, the better your signal will be. But it all starts with current in the antenna, well, current in the radio and the antenna, causing magnetic waves and consequently electric E waves and radiating that, and consequently also picking it up. I want to try to pull up oops. Try to get back to the, okay. Well,
Guys, I will tell you that as an example of what he's talking about, there are people that for grins decided that they would try using the gutter on their house. And they have attached coax to it and taken the steps necessary and actually used the gutters on their house as an antenna, and it worked.
okay. Sorry about that. I had a video. What I would recommend is Google Wiki Dipole Antenna. Wiki Dipole Antenna. And there's a great graphic showing the currents, the E waves and the magnetic waves, and the propagation directions on the antenna. Thought I had it saved, but it's wandered off on me. Now the feed line, obviously you have to hook, with the exception of an HT, you have to hook your antenna up to the transceiver with something. Your HT, obviously you plug the antenna right in the top. Or if you wish to use an external antenna, then you need the feed line. The feed line and the antenna are the antenna system, and they have to function in cooperation with each other and achieve some level of matching. We'll talk a little bit about test and matching equipment, which it allows you to monitor and optimize the antenna system performance. And let's go ahead and get you a full screen again. So, okay, some vocabulary. An element, an antenna element is the conducting part or parts of an antenna designed to radiate or receive radio waves. It's kind of obvious, but a driven element is one of the elements, set elements that is directly connected to your transceiver. You can have some other elements, which we'll discuss, that aren't. An array has more than one element, and they can be driven or they can be parasitic. A parasitic element does not connect directly to a feed line. It's just coupled inductively to the driven element. And Yagi would be a classic example for that. Antenna resonance. Resonance is when the feed point impedance has zero reactance. That's just, there's no inductive, no capacitive element. It's all purely resistive. And that leads into our discussion of SWR in a little bit. And the feed point is where you actually hook the coax or twin lead or whatever feed line element materials you're using. That's where the transmitted energy enters the antenna. And we are talking about radiation, not radioactivity. The antenna doesn't radiate anything when you turn off the electricity, unlike a radioactive source. And radio waves are electromagnetic waves. Now, I think Ron discussed some of this, but electric and magnetic fields are at right angles to each other, and they oscillate at the wave's frequency. They spread out into space from the antenna, and it's created by an AC current. And that wiki diagram really shows that nicely. And I highly encourage you to do that Google Wiki dipole antenna. Wave and current have the same frequency. They're locked together. They can't wander off and do their own thing. And here's an illustration that the blue in this case is the E wave, and the red is the magnetic wave. Magnetic, and they're at right angles to each other, propagating to the right. Now the E wave, vertical, when the E wave is vertical as it is here, then you're vertically polarized, and that would be with a vertical antenna. So the polarization of the E field directly follows the orientation of the antenna. A horizontal antenna is a horizontally polarized signal, and a vertical antenna is a vertically polarized signal. And here we basically say the same thing again. The electric field component with respect to the surface of the Earth is the orientation as is described vertically or horizontally. Now that signal can become circular if the orientation twists as it goes through space and refracts through the ionosphere. And then the signal's polarization becomes elliptical. And in a case like that, it doesn't matter whether you're transmitting and receiving with a vertical or a horizontal antenna. You can pick up a portion of it. Cross polarization. In this case, the antenna and wave polarization must match for maximum reception. If you're cross polarized at perfect right angles, you can virtually eliminate the reception completely by reducing it by a factor of 100. That would basically be probably direct wave only. Once you've got a bounce, once you've got a skip, a hop, your signal is going to be somewhat elliptically polarized, and it won't matter whether you have a vertical or a horizontal at the other end, no matter what you're transmitting with. Antennas are, their gain is expressed in dB, the decibel, and the 10 log power ratio, 20 log voltage ratio. That's nice to know, but in practice, 3 dB doubles your power, 10 dB increases it 10 times. So 3 dB and 10 dB are the more common values that you need to be aware of. For the sake of the exam, you just have to be aware that we express the antenna gain in dB. That's I think the only significant point in this exam. It gets a little more involved later on in other levels of other upgrades. The gain of an antenna, the apparent increase in power in a particular direction by focusing radiation in that direction, and it's measured in decibels in dB. And what it really means, it's a lot like a reflector in a flashlight. If you take a bare bulb and stick it in the air in the night, it's going to radiate in all directions like a vertical antenna, for example, and the signal is going to get weak pretty quick. But if you put a good quality reflector on it and focus it in a direction, in that direction, you're going to get a significant amount more light. Same energy being fed to the reflector or being fed to the light bulb, the element or the antenna element, but the effect of what's felt at the receiving antenna is increased. The isotropic antenna is an antenna, a theoretical antenna that radiates in all directions. It would be like a perfect point source in space, free of solar wind, radiation, magnetism, anything. It would just be completely and totally isolated. And somehow you magically put the power in because it doesn't truly allow for a feed point. But that energy is radiated in a complete spherical pattern. And this is the theoretical standard reference antenna against which all others are measured. Well, not you can actually measure with actually it's a ratio. The dB, the gain in dB is a ratio of anything to anything, but the isotropic antenna is the reference standard. Now, a dipole antenna has some directional characteristics. It radiates primarily broadside to the wires of the antenna, and both and basically in all directions broadside to it. So it's focusing the energy a little bit. It has a potential net gain of approximately 2.15 dB over an isotropic antenna. And some of the higher gain antennas reference gain over a dipole or gain over the isotropic. If you're referencing the isotropic, you have a bigger gain number. Anyway, it's the reference that upon which all the others are based. Now, an omnidirectional antenna has no preferred horizontal direction. This is typically a vertical antenna. It doesn't radiate very much up. It has a very little output vertically, but it's all sent horizontally, but it's in all directions. A directional antenna, as we discussed a little earlier, actually focuses the radiation in specific directions, and the more focusing technology you put in an antenna, the more apparent gain that it has and the stronger the signal will be. And you can hear some of these guys with their big beam antennas at 100 feet with 1500 watts, and they can kind of talk anywhere they feel like talking most of the time. Seems like, but I guess in reality that may not be completely true, but sometimes power is good, but the quality of your antenna probably has more to do. Now, they don't show the antennas that we're talking about. We're really mostly concerned with vertical or dipole in this exam level. This antenna has a radiation pattern. We're looking straight down, bird's eye view. It has a radiation pattern that is much more intense to the right and up and well, 180 degrees of a little more than 180 degrees of radiation pattern, and virtually nothing off to the left. It has a very, very low output at that level. It's not no output. I accidentally bothered a station trying to do some DX work. I didn't hear his DX call, but I was talking on the backside of his beam, and he was in California. So you could still get some radiation on the back end of a beam antenna. And this graph is calibrated in dB, in decibels again. A little more vocabulary. A null is the direction of minimum gain. The preceding illustration, the direction to the left was the minimum gain point, or a null. A lobe is a region between nulls, and there's an upcoming graphic that shows that better. The main lobe will have the highest gain, and side lobes will be other than the main lobe. Forward gain is the gain in the direction assigned as forward. In the case of the previous diagram, that would have been off to the right. Now, an azimuth pattern that shows the gain in all the horizontal directions around the antenna. That's a bird's eye view. An elevation pattern is a side view. You're looking at the antenna from ground level at a distance, and describes where the most of the energy is going, or where the energy is going. And it, yeah, above the horizon. You get a ground wave off some of these antennas, but the bulk of the energy is radiated up at an angle. And in this case, the previous and this pattern, we look at this is the azimuth view, but we look at the elevation pattern, and it's got a lot of energy going straight up. That's not going to do very much good for anything. But these are radiating at an angle, and they're going to run out. They're going to bend through the ionosphere, pull the skip or hop, and come back down some distance. So these lobes, if you have an antenna with many, many lobes, there'll be null spots. You won't talk to anybody on the null, but sometimes that node will, one of the small nodes will you'll still make some great contacts with it. You just won't have a broad coverage with that antenna. And this kind of thing changes dramatically on a dipole with elevation. A dipole antenna has the most uniform pattern at approximately a half wavelength in height when you raise it above the ground. So a 10 meter wants to be 5 meters above the ground nominally, and you'll get the most uniform pattern as a result of that. If you're lower or higher, that pattern will change and the impedance of the antenna will change. And sometimes we use that to our advantage. A front to back ratio is the ratio of forward gain to the gain in the opposite direction. And front to side is similarly the forward gain to the right angle gain. The antenna we just looked at, obviously there's a significant higher output here to there, but it's not so dramatic here. You're still getting a considerable amount of gain off to either of the side lobes. Okay, feed lines. The purpose of the feed line is to get RF power from your station to the antenna. And we have several types. A couple of the common types are coaxial cable or open wire line or ladder line. Power that's lost as heat in the feed line is called loss, line loss really, and it increases with frequency. For a given piece of wire, the higher the frequency you operate, the more loss you'll have. So the quality of your line becomes much more important with a higher frequency. HF is not quite as fussy.
Hello.
Okay, a little vocabulary. The center conductor is the central wire.
I am not.
The dielectric is the insulating material that surrounds the center conductor. The shield is braid or foil or both that surround the dielectric. And the jacket's the outer plastic coating. Now, forward reflected power is the power that travels toward the antenna. The reflected power is the power that's reflected back from the antenna or from an impedance change in wiring. Any change in the transmission line can also reflect some energy back. This energy comes back to the transmitter and is re-reflected back towards the antenna, minus the heating loss in the wire. You have a little bit of IR, so-called IR loss. It's the resistance of the wire, and the current generates some heat, some small amount. Hopefully not enough to literally warm up your wire, but it does reduce the amount of power that can be sent back to the antenna. So the more reflected power you have, the greater the losses you're going to suffer, the greater the line losses you're going to suffer, because that beam bouncing back and forth has to travel farther in the line. It's just, you want a minimum amount of reflected power. And most of the common feed line, the most common feed line to use is coaxial cable. It's relatively inexpensive. It's easy to use. Because it's shielded, it's not affected by nearby materials. So if you're running it along your rain gutter before you go in the house, that rain gutter is not going to affect it. It has higher loss than open wire line at most frequencies. The standard, the gold standard, is air insulated hard line. It has very much the lowest loss, but it's also the most difficult, expensive, and tedious to maintain. Here we have some 4 different coaxial cables. The one on the left is some RG58. It's a 50 ohm cable, but it has relatively high line loss. You don't really want to use very much of this in any setup, because you will lose a lot of signal on it. I had a QRP rig connected to a dummy load with 25-foot piece of RG58, and I had a 50% loss in power. So it can be significant. The next cable is RG8X, and 8X is very common. It has reasonable loss levels, line loss levels. It's relatively inexpensive, and for HF, and up to the low VHF bands of 10 and 6 meter, it's pretty good. Very, very common. The next one is, this is in this case RG8, and as you can see, it's considerably larger than the 8X and the RG58, and it's consequently a superior cable. It has lower loss than either of the other two. It's still not terribly expensive. It's much stiffer. It's not near as flexible, so you have to be a little more careful laying it and setting it up. And the stuff on the right, I don't think I'd want to, that's about 1 inch in diameter. I don't think I'd want to be stringing that around very, very far, but I'm using that in a mag loop antenna, heliac stuff. Now, open wire line is lighter and less expensive than coax, and it has lower loss than coax at most frequencies, but it's more difficult to use because you have to be careful what it gets next to near. You don't want to run it across the ground or next to a piece of gutter or anything that can couple to it inductively or capacitively. And it requires impedance matching equipment to use with most transceivers. Now this is some 300 ohm twin lead, and it's the one on the right is in its native mode with a set of rabbit ears. It's where most of us have seen it. Now the one on the left is actually a J-pole antenna. It's just kind of wrapped up, but it's made with a piece of 300 ohm twin lead from an FM antenna from Ace Hardware. That's what happens when I'm left unsupervised for very long. Our connectors that we use on these systems are predominantly a UHF, so-called UHF connector, a PL259 and an SO239. Virtually all of our equipment, with the exception of our HTs and some of the very high frequency stuff, use this. It's just far and away the most common connector. It's inexpensive, it's easy to use. It is not particularly weatherproof, and it's not particularly good at higher frequencies. But for HF and low VHF, it's very adequate. And the amount of loss that it does present is really minimal if you don't try to make too many connections. On the left is the N-type connector. Now this is on a mobile rig. It's a VHF UHF rig, and it came equipped with a proper connector for UHF frequencies. A type N connector is specifically very superior to the so-called UHF connector at UHF frequencies of 400 megahertz and above. It's also much more weatherproof, and you can look at it physically. You can tell it's a much better design or much more finely constructed device. But its main selling points are more weatherproof and superior at 400 megahertz and up. Those are test questions. That's a typical mag mount for your had a discussion about trying to use an HT in a car, and if you're in the car, the body shielding is going to attenuate that rubber duck antenna substantially. You won't have very good results. You might put it near a window or stick your head out the window with it, but it's not going to give you very good results. A magnetic mount antenna with on the exterior of the vehicle will reduce the amount of noise you pick up and greatly increase the range of your HT. You'll have to get an adapter to go from a UHF, not N-type, but UHF style connector to the SMA connector that's on your handheld unit, or possibly BNC. Some of the earlier handhelds had a BNC connector. This is the tape measure antenna. It's a 3-element Yagi. It's a directional antenna. It's a directional antenna like a quad or a dish. It focuses the beam away from you in this particular situation. Now this is situated horizontally for the sake of demonstrating it, but if you're trying to reach a repeater, you'd want to align it vertically so that your polarization would benefit your signal output. These are kits available at the club. They're like $10. And it's fun and it's functional. And you can break it down, fold up the tape, and tuck it into center holes and store it away in a small area. Now this is a little bit hard to see. That's not toilet paper. That's a paper towel roll. That is a ground plane vertical. And you see the toilet paper roll is a little over a foot, I guess around a foot. This is a 19-inch. That's another magic number in your test. A 19-inch VHF 146 megahertz antenna. The 4 radials, by bending them, changed the SWR on that antenna. You tune it. It's one of the ways of tuning it in addition to making it the correct length. To be actually useful, it needs to be mounted at a height, preferably 10 or 15 feet or more. This is just an old military pole and a little different view of it. And then stuck on 2 poles. I don't know what's going on here, some weird projection of the picture, and I usually put it on 3 poles and then just clamp it to the gutter of the house and get it up high enough that it does some good. Characteristic impedance is the impedance presented to a wave traveling through a feed line. It's a little hard to visualize. It's measured in ohms and symbolized with Z sub 0. And it depends on the physical construction of the material. And typically coax is 50 ohms or 75 ohms. We use 50 primarily, but 75 can be used with some matching equipment. And open wire line is usually 300 ohms. That's your standard twin lead on a set of rabbit ears or something. Or ladder line, which is a little wider, a little physically larger, 450 ohms and 600 ohms. And there are some YouTubes out there on making your own open wire line if you ever have an interest in playing with that. Standing wave ratio. This is a pretty hot topic in a lot of areas, and it's important to protect your transmitter more than anything. We measure the standing wave ratio, and we take the lowest value as the so-called resonant point of the antenna. This is close, but perhaps not exactly true, but close enough. What you want is an impedance that matches the whole system to match. 50 ohms, 50 ohms, 50 ohms is what you'd be looking for. 50 ohms on the output, 50 ohm cable, and a 50 ohm antenna. And you would have a theoretical 1-to-1 SWR ratio. It's sometimes called VSWR. It's a voltage standing wave ratio, but SWR is sufficient for our purposes. So basically, if the antenna feed point and the feed line don't match, some of that energy is reflected back towards the transmitter, and I call that a mismatch. The forward and reflected waves bouncing back and forth in the feed line create a pattern of standing waves of voltage and current in that line. And the SWR is the ratio of the standing wave maximum to the minimum. And we usually measure that with an SWR meter or SWR bridge. And the bridge really more refers to the internal structure of the meter. Okay. Okay, go back one more here. The reflected power, when it comes back from the antenna back down the feed line, comes back to the transmitter and bounces again to the feed line with a loss, a heating loss, because it had to run through the wire. And it's a little bit weaker when it hits the antenna again and bounces back, sends some of it through and bounces back and runs back and forth, heating up your wire, basically. And some of the energy gets out, but you don't get as much as if you had a perfect match and there's no reflected energy or very little. Eventually, it uses all the energy up, and it either goes out as heat in your feed line or radiates from the antenna as a signal. The high SWR means more reflections and more loss and less energy to your antenna. So to that end, it's very important. It's very unusual to have perfect SWR. SWR is the ratio of the feed point or load and the feed point impedance, whichever is greater than 1, and it's always greater than 1. And so what is acceptable? 1-to-1 would be no reflected energy and everything went out the antenna. And that's extremely rare. Up to 2-to-1 is considered normal and acceptable. And it actually defines the bandwidth of your antenna. If you plot the SWR values, SWR is perfect at a frequency, but you change your frequency ever so slightly and the SWR is going to change. So the range or bandwidth of your antenna is based on the 2-to-1 points. So if you just back off lower and higher on the frequency and look at the SWR measurements, the bandwidth is the range between those 2 points. There'd be a 2-to-1 point at a lower frequency and a 2-to-1 point at a higher frequency. And modern radios protect themselves if they see too much SWR, and that's typically when it goes above 2-to-1. That's a basic 2-needle SWR/power meter. And we can see one needle measures the forward power, and the other needle measures the reflected power. And then we can figure SWR based on the intersection point of the two needles on one of these lines here. Very, very handy thing to have on your radio at all times. Now, SWR above 3:1 is generally considered high. Many modern transceivers have an antenna tuner that'll compensate up to 3:1, protect the finals, allow the final to operate at full power, and let you continue to transmit. You still have the SWR problem out on the antenna feed line system. It's still out there bouncing around, but it will protect your radio. Now, if you get erratic SWR readings, if you keep and there's a meter on your radio, but it's normally not as sensitive as a good external meter. That may indicate a faulty feed line, line connectors, or antenna, corrosion, water intrusion. There's a number of fault modes that can affect your SWR reading. I had a SO239 socket loosen up to the point where there was no connection whatsoever to the pin on the PL259. But when I scanned it, I got some signal up at or some apparent response on that antenna up in the high 35, 40 megahertz range. And what was happening is that open connection actually acted as a capacitor and would pass energy at the high frequency, but it wasn't usable. And the connector had to be replaced. So you can correct this by tuning or adjusting the antenna. And the most common way, especially with a dipole or a vertical, is to change the length of the antenna. Long antennas are lower frequencies, short antennas are higher frequencies. If you want to make the resonant point go up, you shorten the antenna. If you want to make it go down, you lengthen the antenna. And get the best SWR you can and shoot for less than 2:1, and then you're probably rocking. You can take an antenna that when it's at its best, or you're running at a different frequency, and you can use an antenna tuner or transmatch to operate with a less than perfect antenna, and again, protect your transceiver, your amplifier, but it does not change the SWR in the feed line. You'd still be heating up the line, and a lot of the energy would not be getting to the antenna for radiation.
I have a quick question if you have a moment.
Definitely.
Is there an easy way to measure SWR as you're setting up your own system?
To measure SWR on?
An easy way to measure it.
So you're setting up a radio, you got your feed line, all that fun stuff. How do you actually measure what the ratio is?
Well, you can do a couple of things. The first, your transceiver has an SWR meter, usually. You can use that by transmitting on a clear frequency, preferably CW, but FM will work. At a lower power, turn your power down. You don't need 100 watts out of a 100-watt transceiver to see the SWR. It doesn't change with power, so turn the power down and look at your SWR meter. Now, if you keyed up and you saw 2.5 to 1, and you were on 28.150 megahertz, say, and you keyed up and you found a 2.5 to 1. Take your frequency down, be sure it's a clear frequency, and see if it improved. take it up and see if it improves, see which way it gets better, see which direction the frequency makes it better. If you need, if the antenna is resonating at too low a frequency, you need to shorten it. And go out and shorten it by an inch or two, the ends, depending on the length of the antenna. You get sound at the very end, you can be trimming a ½ inch or folding. What we usually do is fold the wire back. And if you fold that back, I'm going to do that in a minute with a real antenna. If you fold the wire back over and wrap it around itself and it's bare wire, then you will effectively change the length of that antenna. Or you unwrap it and extend a little bit of it. Ordinarily, when I'm setting up a dipole, you should leave excess wire on the dipole to begin with, fold it back to the calculated length of the antenna that you would expect, and then measure it again. Now, another way to do that is to get an external SWR meter, and they can be had for fairly inexpensive, but today, there is an antenna analyzer for $50 that plots the quality of your antenna and shows you the frequency, resonant points, and all kinds of things. And it's a nano VNA. And that's my favorite test piece. It's $50. I mean, it's amazing. You can't buy a VSWR meter for that from any of the big boxes. But in any case, you can still use the meter in your radio. If you take wire that's insulated and you fold it back over on the end, it still affects the length of the antenna, but not as dramatically as if the wire's bare at the end. But essentially, look at your SWR meter, move the frequency and see which way it's happier. And if the frequency is lower than you want, then the antenna is too long. If it's higher than you want, it's too short, and then you go back and make the adjustment. And we'll look at this some more here in a few minutes. Does that help?
Yes.
Any other questions? Anybody, please interrupt and ask them, because we can pick up with this anywhere, anytime. We're almost through the slide set anyway. Okay, so if you have an SWR meter and you want to hook it up in the system, this diagram shows an antenna tuner, the meter, and your transceiver. But in my case right now, I don't have an antenna tuner. The only one I have is embedded in my radio. I would eliminate the antenna tuner and put the SWR meter in, and then I can play with the wire on the end to tune it to get a good reading. As long as I get it under 2 to 1, I'm probably good to go. But I like to get it better if I can. But if you have an antenna tuner, whether it's in the transceiver or not, it'll compensate for whatever little bit is left over and make your radio happy and protect your radio. Not going to change the antenna feed line system out here, but it's going to protect everything back on the left. And that brings us to dummy loads. And this is really one of the last topic on our slide set. A dummy load is nothing more than a resistor with a heat sink or not. And it's theoretically the perfect antenna. It's a VSWR of 1, perfect. Just doesn't radiate very, very much. So it dissipates the signal as heat. It doesn't dissipate, well, the way this is phrased, it takes the feed line energy and it all passes into the resistor and is consumed as heat. It allows you to test your transmitter without sending a signal over the air. And I suppose supposedly it's helpful in troubleshooting an antenna system. I don't know if they actually have a question that resembles that or not. That'll let you know if your if you're having issues, you plug a dummy load in, and if your radio's happy, then yeah, you got a problem with the antenna system. You need to go look at the SWR, make sure all the connections are good, a tree didn't fall down on it. In the case of a vertical antenna with ground radials, if the squirrels didn't chew them all in half, and I have a problem with that. I've got 3 or 4 of them might have been literally cut in half by squirrels. I don't know why they like that wire, but they do. They come in many shapes and sizes. These little guys up front are basically terminators. The one on the right is a 75 ohm that was used to terminate video systems where you have multiple monitors, but it can function with a QRPP rig if you had a 75 ohm need. The one on the left is a 50 ohm, and that actually, I've used that with a Pixie CW transmitter, 200 milliwatt transceiver. Doesn't take very much power to burn that out. It's only a half watt. These little guys laying on the table are 50 watt, 50 ohm resistors. They're designed to be screwed to a heat sink. And unfortunately, the heat sink, this tab is part of the electrical circuit. So you have to consider what you're hooking where in order to get the right amount of resistance and not short anything out. This thing here on the upper left is a homebrew that I did after I was kind of down after a surgery. So I'm going to blame some of the soldering on the pain meds, but I had a whole roll of 2200 ohm resistors. Back to your electronics, these are red, 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 gold resistors. That's 2, 2, and 2 zeros, and 5%. So they're pretty close. It turned out I needed 42 resistors. So that all that in parallel equals 50 ohms. And it gives me about 20 to 25 watts of power possible. Now, if I submerge that in oil, there are antenna dummy loads called cantennas from back in the day with a 1 gallon paint can and resistors in insulating oil that'll handle 1,000 or 1,500 watts. The other dummy load is a QRP Labs 20 watt dummy load, and it's got 20 1K resistors, 1 watt 1K resistors. Nice little kit. If you want to try a good beginner kit to build, this is a great and useful kit. They have a diode and a capacitor in there that produces the DC voltage out that goes back here, in this case, to a connector so I can plug a meter on it and read in volts a relative power reading, and then there's a correction factor to calculate the power with it. So it's pretty handy. And that's the end of the slide set. Now, if we look at be careful not to let's see here. Yeah, it's not being cooperative. All right, well, what I've got now is okay. All right, here we go. Should switch over. Okay, let's stop the share. All right, let's see if we can get to it now. I will figure out how to use this silly thing one day. Okay. All right. So now with a technician license, you have full privileges. You have full privileges on on 6 meters. So what we're going to do is build a 6-meter antenna in about 5 minutes. I've done a little bit of prep work on it, so it won't waste very much of your time. If you're going to have a 6-meter antenna, you need to figure out the length. In the study guide, they probably talk about dividing 468 or 482, something by the frequency in megahertz. And that gives you the half wave. But I find it easier to just remember 234. If you divide 234 by the frequency in megahertz, it will give you the length of one element of a dipole or a quarter wavelength of a vertical antenna. So what I've done is I've measured out. It turns out that if you take 50 megahertz and 234, you get 56 inches per element, or 112 inches. Just on the test, 112 inches for a 6-meter dipole antenna. And this is at 56 inches. When I wrap the wire back like that, we can hook a piece of string, hook something on the end to tie these ends up. But we've got to hook it up to the coax on the other end. And what I have here is a European style barrier strip, and you can pick these up online real cheap, $1 or $2 for a multi connector barrier strip. But you can build a perfectly legal antenna with nothing more than a couple of wing nuts if that's all you've got available. Connect them together, or if you have a soldering iron, solder them together, tape them up real good, or if you have a barrier strip, oops, gravity check. My first antenna was virtually this with the soldering option. I soldered a couple of light wires to the end of my coax because I didn't have very many at the time, the PL259s. Okay. All right. Now, if you tape all that up, a nice job of making it secure with tape so that it'll be reinforced. In this case, I've got a BNC cable. If you have a BNC style transmitter, like a little Pixie, or use an adapter to convert, or get the PL259 for this end of the feed line. This is all you need. The ideal height for a 6-meter antenna is a half wavelength. So that's 3 meters. That's a little over 9 feet, so about 10 feet in the air. If you had a 10-foot piece of 10-foot PVC pipe, that would be sufficient for the center. Just tape it all in the air and stick it over a piece of rebar or something, or to get a few pieces of string, make some guy lines, take the 2 ends and pull them out. And if you have something convenient to tie them off on so that it's horizontal, that'd be great. If you don't, you can just droop them down in the form of an inverted V. And if you make an inverted V, the pattern changes a little bit and the impedance actually improves. You'll get a little bit more omnidirectional pattern from it. And that's handy. Yeah, I mean, you don't need to use anything fancy, just some garden variety string to tie it up with. If you ever get to a show again, you might find some little insulators that you can use, but you can use PVC pipe, old printed circuit board, or just use the string. Now, that will put you on 6 meters on the air with all benefits and all privileges. So if there's any questions on that, you can get a little more. You can get more exotic, obviously, and you will, and you'll change your mind multiple times about what's the most fun and what you want to run. But I am going to string this up because I haven't played on 6 meters. Okay, are there any additional questions? On the website, there will be a couple of PDFs that we can give you some summary of basically of all the answers in reality on 3 pages. So